Hi, welcome back to Sam's Maths Lectures. So we're going to be talking more about path integrals today, and we're going to be still not doing path integrals. We're going to be generalizing our Gaussian integral from last time sort of further. So we're going to start by looking at what we had last time. So we had this integral, very general integral in n dimensions, where m here is a positive definite, so all eigenvalues are positive, symmetric matrix. And so this integral here is equal to this, and we're going to call this z of j. For reasons that will become apparent later, hopefully. Okay, so let's talk about some important properties. So first of all, we're going to stop using m inverse. It's just a bit clunky. So we're going to write delta equals m inverse as just a new symbol. Save me writing as much. And then what else are we going to look at? Let's talk about the determinant. So the determinant, obviously, if we're working over an actual matrix, that's fine to use a determinant, but when we move on to functional integrals, m is going to stop being a matrix and start becoming a sort of bilinear functional. And the determinant of a functional is kind of weird to talk about. It's just hard to visualize based on how we define a determinant in linear algebra. So instead we're going to think that, well, the determinant of m is the product of its eigenvalues, which is then the product of the eigenvalues is the exponential of the sum of their logarithms. Right. So that's another way to write it. But then the log of lambda I, these are actually the eigenvalues of the log of m. If you can think of log m as a matrix, which you usually can using diagonalization. And so this is e to the, well, the sum of the eigenvalues is the trace. So the trace of log of m. That's a functional determinant. That's something that's more manageable to work out once we work out what log m is. Then the last thing we're going to do is we're going to talk about differentiation. So the derivative with respect to ji of zj is, so this thing here we're going to call z of 0, because when j is 0 this thing goes to 1, so we get z0 as our constant out front, just for shorthand. So that's z0, and then we just differentiate the exponent with respect to ji. So d dji 1/2 j transpose m inverse, we're calling that delta now, j, and then times by e to the half jt delta j. Now, what is this? Well, half jt delta j is 1/2 j subscript j, so the jth component, delta jk. I'm going to be using Einstein's summation convention, so if there's a repeated index, we're summing over it implicitly. Usually, not always, there will be cases where we're not doing that later. But for now, just as shorthand, so this is sum over j, sum over k. And so when we differentiate that, we can put the sum in here. Why not? Sum over jk. So we just do the product rule, so the half is not going to be differentiated. Delta jk is not going to get differentiated because that's just a number. And then ji by dji is just delta ij. So that's 0 if they're different and 1 if they're the same, because obviously if I and j are different, then the two j components they don't depend on each other. They're independent, whereas otherwise they're the same thing, so the derivative is going to be 1. So we get from differentiating jj we get delta ij jk, plus from differentiating jk instead we get delta ik jj. If we, for this one, we do the sum over j, we're going to get 1/2 delta ik jk, sum over k here, plus if we do on the other one we do a sum over j instead, sum over k, sorry, to eliminate this delta, then we're going to get 1/2 sum ij jj. Now k and j are dummy indices, so that is just 1/2 delta ij plus delta ji ij jj, which is just delta ij ji jj. Yep, there we go. Sorry, put in mind like that. So we start with it written out as a sum in full. We get these delta functions, then we sum over the delta functions, then we just replace our dummy variable, because this is a sum over k, this is sum over j, we can just relabel our sum variable. We can then merge them together, and we end up with the matrix element times a dummy variable. So then dji of zj is, we're actually going to leave it in zj form, so it's delta ij jj zj. That is a lot of j's, I'm aware. Okay, so now let's start using our Gaussian integrals for something. It's not going to seem related to field theory at first, but it will come up later. It's just I prefer looking at it in finite dimensions and using matrices first, just to sort of motivate things, and then later we'll sort of look at it and say, well, this is clearly the same. We can now transfer this over to functionals easily. So what we're going to do is we're going to have a probability distribution in n dimensions f of x equals 1 over z naught e to the negative half x transpose m x. This is a perfectly valid probability distribution. It's just an n-dimensional Gaussian distribution. If we now, what do we want to get from our probability distribution? We probably want to get expectation values. Everything really can be pulled out of expectation values. So let's start by looking at the expectation value of xi. This is going to be 1 over z naught. That's our normalization to get rid of the square root thing. Integral dnx xi e to the negative half x transpose mx. And this is 0 because m is symmetric, which means that our distribution is symmetric around the origin. So xi, the expectation value, is going to be 0. You're equally as likely to get this thing at plus 10 as minus 10, and so on. So it's going to cancel. That's boring, I know. But now let's move on to xi, xj. So the product of these two things. We're hoping this is not going to be 0 now. So this is going to be 1 over z naught integral dnx xi xj e to the negative half x transpose m x. Okay, well that's that looks doable. Maybe we could do some clever integration by parts to work this out, but we're going to be smarter than that. We're going to use a different approach that's going to basically give us an easier answer that we can generalize more easily. Now, if we instead write f xj as e to the negative half x transpose x plus j dot x. So our probability distribution is fx naught. Then what we see is that df by dji is going to be, well, there's a ji in here. It's got sort of ji xi in the dot product is xi f xj. That's convenient because then that means that df by dji evaluated at now j equals 0 is going to be xi f x without the j, because we eliminate our j term, that just goes to 1, the e to the j dot x. So we can write that expectation of xi xj is 1 over z naught integral dnx, not xi now, d by dji d djj of f of x j evaluated at j equals 0. Now the integral is respect to x only, its boundaries don't vary or anything, so we're free to take the derivatives through the integral, and we can also take the j evaluation through the integral. Right, the integral is only cares about x, it doesn't care what j is, so whether we say that j is 0 inside the integral or after we do the integral doesn't matter. So we can say that this is 1 over z naught d dji d djj integral dnx f of x j, and then all of this evaluated at j equals 0. Now this is just our partition function zj, and so we end up with 1 over z naught d dji jj zj at j equals 0. This is good. This looks like something we can get a handle on now. So 1 over z naught, well, we now know how to do that derivative with respect to jj. So this is d dji of, and so this is just going to be delta jk, k is a dummy index here, jk zj, and all that is at j equals 0. Now when we do our ji derivative, what we're going to get is we're going to, obviously we've got a product, so we're going to differentiate this thing, and then we're going to differentiate this thing. Now when we differentiate zj and leave the delta jk alone, we're going to pull down another dummy index j, so we're going to get a delta iljl, and it's going to multiply by this term, but that's actually going to vanish because we're going to set j to 0, so any j's left over are going to, any terms multiplied by those will get removed. So we only have to differentiate this term, and that's nice and easy to do because this is a constant, and then we differentiate this by ji, we get delta ik, we sum over k, we just replace all of our k's by i's, and so we end up with 1 over z naught delta ji zj evaluated at j equals 0, which means that we get a z naught there, and we end up with delta ji. So if ji is non-zero, so there's a correlation between xi and xj, then we end up with a non-vanishing expectation value. So that's a fairly easy case. Now we're going to do something a bit more involved. I hope that I end up getting this all correct. So the expectation value of xi, xj, xk, xl So I hope you'll let me generalize my previous argument to say that this is going to be 1 over z0. And then we just take 4 derivatives, ji, jj, jk, jl of zj at j equals 0. I'm now, just for shorthand, I'm going to stop writing this and I'm going to stop writing this. They're there on every line, but you don't want to watch me write every single line of that. I don't want to write every single line of that. We're just going to pretend they're there without me writing. Okay, so let's start with the JL derivative. So we keep our first 3 derivatives, dji, djj, djk. And so we differentiate with respect to JL, and we're going to get sum LM JM ZJ. Now, when we have something like this, we've got something times ZJ. When we do our product rule, we can sort of think of it as everything that's already multiplying ZJ is going to get multiplied by a new dummy index sum, right? So we're going to get a delta Kn Jn multiplying this thing, and then everything not the Zj, so this, is going to get differentiated with respect to Jk as well. We add both of those two things together, multiply the whole thing by Zj. Right, so I mean, if you watch me go through it, hopefully that'll make more sense. So d2, dji, djj. So what's already there gets multiplied by a dummy index. So j delta lm, jm, delta kn, jn, and then everything that was already there gets differentiated with respect to whatever we're differentiating with. So plus delta KL, right? Because this is going to be a delta KM, we sum over it, we get that ZJ. We do it again, so we're going to get a DDJI left over. Everything inside is going to get multiplied by a delta JP, but, right, this term we're not going to bother writing in. So, because we've only got one derivative left, we don't want too many extra terms that will get killed off by the j equals 0 condition. So if we leave this term in and multiply it, we're going to end up with a cubic in j. We can differentiate that once, well, that's going to go down to a quadratic. That's still going to vanish when we set j equals 0, so we're not going to bother writing it. This can be multiplied, so we get delta KL, delta JP, and then we differentiate these things. So this, obviously the derivative with that's just a number that's going to vanish. This we can differentiate, and we get 2 different ways to differentiate it. So either we can differentiate this one, and we get delta LJ, delta KN, JN, or we differentiate the other one, and we get delta KJ, delta LM, JM, all times ZJ. Now, one more derivative. We're not going to multiply anything by delta IQ, JQ, because that's going to vanish when we set j equals to 0. So all we do is differentiate these things with respect to ji. It's going to give us delta KL, delta JI from the first one, delta LJ, delta KI from the next one, plus delta KJ, delta LI. And then times ZJ, but then that's we're now taking j equals 0, so that's a Z0, it cancels with the other Z0. We end up with this. Okay, so we've worked it out. We just take our 4 coefficients. I don't know. It might be 4. A bit embarrassing for me. 6. We have 6 different coefficients. We multiply them together in different ways. we end up with our expectation value. Obviously, there is an easier way to do this. I knew the answer without having to go through all that maths. But before I introduce the easy systematic way to do it, I want to go through one more example. Just to show where we're coming from, and then I'll present this diagrammatic technique for calculating these sums. So now, finally, we're going to do xi, xj, xk, but we're going to put this to the power of 4. We're going to find this expectation value. I'm also going to write partial subscript I for partial j, partial ji. It's just shorthand. It makes this whole thing quicker. So we're going to say this is di, dj, d4k, z, j. And obviously this is divided by z0. It's evaluated at j equals 0. But we're ignoring that for now. Which is di, dj, d3k. I'm going to go through this pretty much in full. So I hope that's not too boring. Otherwise, skip about 5 minutes into the future when the answer falls out. So we're going to get a delta kl, jl, zj. So then we're going to get di, dj, 2k derivatives left. So differentiate everything inside the bracket with respect to k. So that's going to be a kk here. And then add on everything inside the bracket times our new dummy index. So that's a kl. And then we'll have a km, jl, jm, z, j. Which is going to be di, dj, dk. Differentiate everything inside the bracket. This is going to vanish. Then we're going to get a delta kk jm from differentiating the L1 plus delta kk. Oh, that needs a delta in as well. Here we go. Delta kk, delta km, jm, there we go. Plus delta kk, delta lm, delta kl, sorry, jl. And then we multiply everything by our new dummy index. So that's going to be a delta kk, delta k, what's next, n, jn, plus, now it's 3 delta 1, kl, delta km, delta kn, jl, jm, jn, zj. Let's make that a square bracket for consistency, doesn't really matter. I'm going to move along a bit so I've got more space. So di, dj, start by differentiating things with respect to k, so that's going to be a delta kk squared from this one, and then another one. In fact, all of these are going to give us delta k squared, so we get 3 of those. And then we differentiate the other one, we're going to get kl, km, delta kk, jl, jm, plus delta kl, delta kn, jl, jn, plus delta km, oh, missed out the delta kk. Yeah, writing these out in full is not fun. Delta km, delta kn, here we go, jm, jn, that's all of them, and then we're going to multiply by the delta k cube, kp, jp for our new dummy index. But this one is not going to get multiplied because we've only got 2 derivatives left. So we do not want 4 free j factors because that's going to get killed off by the j equals 0. These ones we can add an extra j to because they'll end up with a quadratic, and then that will hopefully get differentiated twice, give us a constant which won't vanish. So we're going to get delta kk, km, delta kp, jm, jp, delta kk, delta kl, delta kp, jl, jp, plus the last one now, delta kk, delta kn, delta kp, jn, jp, z, j. Now it gets considerably easier because we cannot add anything to most of these, right, when we add the z. How am I going to write this all out? Okay, so let's think about this now and try and get this into a slightly less horrible form, because I don't want to do all of this. This term here is a constant, and we already know what's going to happen when we do di dj, right? We've already done that before. It's the expectation value of xi xj, so we're going to end up with 3 delta k squared delta ij. That's that one done. Now all of these terms are basically the same, right? They just have different dummy indices. This one's got an L and an M, this one's got a L and an N, but they're all effectively the same. So let's focus on this one. I'll do it just below. So we're going to get, because we can't add to any of these, so we have to just differentiate. In fact, we'll do it in full. So di dj, delta kl, delta km, delta kk, jl, jm, z, j. And we got 6 of these because they're all the same. They've just got different dummy indices. This is the rest of our sum, right? So this is going to be 6 partial I. So we're going to get 2 different things here, depending on which one we differentiate with respect to j, right? Either we can differentiate the jl or the jm. So we're going to get 2 delta kk, delta kj, delta k, the one left over, jm. And then we don't bring in another factor from our zj because that'll get killed off when we set to 0. So we just leave our zj here, which is going to be 12 times, well, the only thing we can differentiate here is the jm. We can't differentiate the z because that'll bring another the j that will get killed off when we go to 0. So that is going to be 12 delta, I'm going to write it ik, delta kk from this one. Remember that delta is symmetric because m was symmetric. Delta kj. So our whole thing is 3 of these plus 12 delta ik, delta kk, delta kj. Now, how could we get that without going through all this calculation? Obviously it didn't take me too long, but I made some mistakes. It was a bit clumsy. It's very unwieldy. We don't want to do that. We want a slicker way of doing things. So what we do, if we want, we'll do the example we just had. K to the 4. So first what we're going to do is we're going to put a vertex for each index. Okay, so we've got an index I, index j, and a k, which I'm going to put here. X a to the n has a, what's the word for it? Is it valence of an index in graph theory? I think it's valence. N. So valence just means the number of legs we're going to connect. We're basically building a graph. So we connect one leg to I, one leg to j, and we connect up these. 4 things are going to get connected to j. Now what we do is connect all nodes. Now there are basically 2 ways we can do this. Either we can connect I to j like that and connect k to itself, or we can do ij, we'll put k in the middle now, and we connect I to k, we connect k to itself over the top, and then we connect k to j. So these are 2 graphs or diagrams. These are in fact Feynman diagrams. They're a little bit easier than actual particle physics Feynman diagrams, but this is where we're coming from. This is like the easiest form of Feynman diagram. Now, to evaluate each diagram, each leg from A to B gets a factor delta AB. Okay, so that means that our factors for this graph, we're going to get a delta ij from that top leg, and then 2 delta kk's from the 2 legs down here, and here we get delta ik, delta kk, delta kj. The order of the individual bits doesn't matter, but we're going to pretend it does, or write it in a nice way. And then finally we get a symmetry factor. So this accounts for the fact that there are lots of ways in which the same diagram can occur, right? So we could have sort of connected these 2 k vertices, or we could have connected across like this, right? There are 3 ways that we could have made that diagram, and we see that in the coefficient 3 here, right? Because there are, what actually happened was that one of the k's, the k that was given the L vertex, right, the dummy vertices label each sort of valent bit of each node. So one of them was the L and the M connecting, the N and the P connecting. One of them is L and P connecting, and M and N connecting, right? So there are 3 ways we can do that. So for this one it's 3, because ways we can connect I to j, only one way, because I only has 1 valence, j only has 1 valence, one way to make them join. Whereas if we sort of think of these as 1, 2, 3, 4, well, there are 3 ways to choose what one gets connected to, and then the rest of the graph is well defined, because if you connect 1 to 3, then you have to connect 2 and 4. So we get 3. This one, well, we know that I has to connect to one of the k's, so we get 4 choices for that, right? Because I could connect k1, k2, k3, k4. J has to connect to k as well, so J has to connect to one of the other 3. So we get 3 choices for where J plugs in, and then the k loop is predefined, right, by the 2 left over, and so we get a symmetry factor of 12. And then add up all diagrams. Done. So what can we do to sort of work this out? Let's do an example, I guess. We should note that if the sum of the powers that each thing is raised to is odd, get 0 for our expectation value, because when we take our integrand, it's going to be odd, right? Under parity, it's going to get a minus sign, and so it all ends up going to 0. Otherwise, we're okay. So let's try not phi x a x b squared xc cubed xd to the 4 xe xf. Okay, so what do we get here? We get a gets 1, e gets 1, f gets 1, and then we have to connect all these up with a vertex that has a valence of 2, one that has a valence of 3, and one that has a valence of 4. So various things we could do. We could do E and F go together, A connects to C, which connects to itself, and then B connects to itself, and D connects to itself. That's valid. What else could we have? We can have A goes through B, then everything meets at C here. E goes directly to C, but F goes via D, which has this loop. There's going to be a lot of ways that we can make this diagram. I can't think of the total ways, but let's look at symmetry factors for these. So this gets a symmetry factor of 3 for this part, because there are 3 ways that A can plug into C. We get a 3 from this. We know that this figure 8 has a factor of 3. So this thing gets a factor of 9. Delta AC, delta CC, delta BB, delta DD squared, delta EF. That's that diagram. This one, symmetry factors, A can plug into B 2 ways. So 2 ways that A can plug into B. Then B's remaining vertex has to plug in somewhere on C. So that's going to give another 3 for the way B plugs into C. Then E gets 2 choices of where in C it plugs in. Then D is forced to plug into C there, but C has 4 choices for where it goes on D. F has 3 choices, so you get 3 times 4, 12, 36. 36 times 4 is 144. And then what lines do we have? We've got delta AB, we've got a delta BC, delta EC, delta CD, delta DD, delta DF. That's that diagram. And so on. We could work out all of them, but I really do not want to. But we add up all the diagrams, and that's how we would work out this expectation value here. I think that's enough for this one. So thanks for watching, and I will see you next time.